Hey, Professor.
Hey, Jacob, how's it going?
Good. I thought someone else was waiting outside. Maybe he wasn't in that class.
Yeah, I saw him too. He was just watching me open the door.
Do you teach 421?
I don't think so, because I don't know what that is.
Well, I guess it's a class where you design like gears, screws, fasteners,
Ah,
and then I don't know if it's ANSYS, but you do some type of test on it to see how it fails.
uh-huh.
And I mean, that sounds exactly like the type of thing I'd like to learn,
Mhm.
considering like, you know, the skill set that I guess now that I'm trying to aim for.
Mhm.
Because, you know, it's like we offer the most of those classes that work best together, like design and then failure analysis,
Mhm.
which goes with, you know, strength of materials. But then all the other classes are like, there's like two controls classes, there's the 400 level one and the 500 level one.
Uh-huh.
And I'm taking the 500 level one. But even if I take the 400 level one, like I'm gonna have no idea what to do with it in real life because I'm taking the more advanced one and I still don't know what the heck I would do with it in real life. And then the other stuff is like vibrations and like all that. And it's like, okay, how am I gonna apply that in the real world with what I know now? I have no idea how I would. But like 421 sounds perfect, but the only problem is it's not available for graduate credit, and I don't know why. Because it seems like the perfect class for me to take anyway. So, yeah, I was just wondering if you taught that, just because it sounded like something that you would teach, because you teach 540 and then the other finite elements class. So.
Yeah, I do not teach that one. I'm not sure who teaches that one. Probably one of our more structural faculty.
Okay, I'll just have to ask Dr. know what's up with that. Okay, so for number 2, A, I don't know why I'm not getting the right answer. So here, my answer was like 5 newtons less than yours, no big deal.
Fine, yeah.
But here, this one is like 40 something newtons bigger than yours, and this one is like
40 newtons is not.
similarly off.
If it's off by like that, if it's like this third significant digit, then I count that as like the same.
Okay, but this is like 100 maybe off, and I don't know why. Because we have x, so I have my jx going in the negative direction, and then it's just
Yeah, it should just be
fm cosine of 66, right?
It should be 63, right? Because 30 plus 30.
Oh, that's probably why. Although I don't think that would make that significant of a difference.
It might over here. Maybe this, or no, this should be 33.
Yeah, I accidentally put 66 here. I would say, or 60. Yeah, I don't know why I put 66 and not 63.
Yeah, it should just be those two. I would need to double check my answer. So
Okay.
It's in my office. So I'll check it when I get back.
Okay.
Yeah. But that looks right. It's just you just have those two forces in the horizontal direction. So.
Okay, and this is right, just adding these two together. Right?
Yeah.
Okay, and then for the third one, you said, oh, okay, what muscle? Because you have your abs and your lower back.
Yep.
And you say which muscle force is keeping you standing upright?
Yep.
And it's your lower back, right? Because it extends your torso back this way.
It depends where you are. So like for the first configuration, the person is almost like leaning back, and so like the backpack's almost kind of like weighing him down. And so for that case, the abs are actually acting to kind of bring it up forward. So it kind of depends. And so in one configuration, basically the backpack is going to be pulling back like this.
Okay.
But then if you're kind of leaning forward, then the backpack's going to be pushing you down this way. It all depends. It all depends on the position of the backpack relative to the back.
Okay.
Yeah.
So first one's abs, because you're trying to bring your
torso
forward.
Yep.
And the second one, I guess you can bring it back a little bit.
Yeah.
Okay.
Yeah. There's interesting. So third part of that problem, I want you to solve for the angle where like neither of them. So that's actually probably the best posture, because then you make it so that neither of your core has to work to keep you upright. So that actually produces the least amount of stress in the back.
Okay.
Yeah.
All right. Thanks, Professor.
Would you say for that problem, right, like we're saying, have a datum, right, at the lumbar spine horizontal, I just put the backpacks waves also to that. Of it, so I have to use the opposite muscle, which is the abductor muscle. Was that reasonable answer?
Wait, say it again.
Is
Sorry.
that datum? And spinal lumbar spine. I just said since the distance it's negative, this goes positive. Have negative, it's false from the left side of the datum. The abductor muscle to keep it stable.
Yeah.
And since the other situation is when it's on the right side, so I have to use the back extensor.
That's exactly.
Okay, yeah, Professor. It turns out that those 3 degrees make a pretty big difference.
Oh, that's good.
And do you have any idea what you're going to be teaching next semester?
I do not. So they don't give me my assignments until at least after Thanksgiving, probably closer to Christmas. But I can tell you what I'm probably most likely to teach. And so I'm probably most likely to teach 541. I'm also probably most likely to teach 417, which is a computational class. So that one's basically all MATLAB, and we learn how to compute or how to program or how to code programs that solve heat transfer problems. And so I'd say those two are most likely what I'll teach, and then the others it'll depend. But even those I'm not guaranteed, because it depends. because we tend to schedule the part-time faculty first if they're comfortable teaching those really specialized classes. But because I'm here full-time, my schedule is a lot more flexible, so they kind of fill in what's needed.
Okay. Because I can't take the heat stuff,
Mhm.
so.
Finite elements class, do you post the lectures on YouTube?
Yep. Mhm.
Okay, cool. 'Cause I have a final for a class that's right after that one.
Uh-huh.
Not a final, midterm,
Uh-huh.
so it might not be there.
Okay, yeah. I post it all on, it's all, you can find it all from Canvas too, so.
Okay, cool.
Yep. Mhm.
'Cause, yeah, I have like a class, your finite and have a class 15 minutes right after.
I see. That's a late class then. It's a 7 p.m. class.
7 to 8.
Oh, wow, that's late. Yes, the midterms next week. We're going to talk about it a bit today. Yeah. Right. All right, it's 4 o'clock, so let's go ahead and get started. All right, good afternoon, everyone. How's everyone doing today? You have a good weekend? Good. All right, so we're in week 11, and so we are in the middle of doing dynamics, okay? And so our plan for today is we're going to hopefully, maybe not finish, but at least, significantly make a lot of progress on these lecture notes, okay? All right. Some announcements I want to make is that homework 5, remember that one's due on Wednesday, okay? So make sure you guys are working on it. The statics problems are a little bit tricky, and so, I've gotten quite a few questions on those already. So if you're struggling with those, especially with the free body diagrams, then, make sure you reach out, okay? Just like someone mentioned before the class, the backpack one. Yes, the backpack one is pretty, that one's pretty tough. And so, even that one took me a while to do. Yeah, so make sure you're working on it. And if you have questions on it, stop by office hours, send me an email, and I'm happy to help you out with that. Okay. All right. And so just like someone mentioned before the class, we have a midterm next week. Okay, it's going to be next Wednesday. Okay, and so that's going to be in class. No, it's going to be in class. It's going to be in class midterm. Yep, so it's going to be exactly the same as how we took the first midterm. So you guys are all going to come to the lecture hall, or I guess the lecture classroom, and then take the exam in the class. Okay? It'll be the same format, or at least in terms of what you can bring. And so you can bring a 8.5 by 11 sheet of notes. You can bring your pencil, you can bring your eraser. And since there's going to be calculations on this exam too, you can also bring a calculator as well. Okay.
Is it front and back?
Yeah, front and back. Yep. Mhm. Yeah. So it's going to be in class next Wednesday, correct? Mhm. Okay. In terms of the content on the exam, I kind of, went back and forth with this in my mind because, we're just getting started with the dynamic stuff. And I was debating whether to give you guys one more homework assignment no, not this Wednesday. It'll be Wednesday, November 10th. And so I was debating whether to give you one more homework assignment on the dynamic stuff because I really don't like giving exams on stuff that I don't have you guys practice on the homeworks first. But because this homework is due this Wednesday, if I assign one more homework, it would probably have to be due Monday in order to get it in before the exam. I think that's kind of way too short of a lead time, and so I'll hold up homework 6 until after the exam. We'll probably have that due right before Thanksgiving, and then this exam is just going to be on the static stuff. Okay. And we had and joints too. Statics, all the static analysis stuff and joints, joint biomechanics. All right, question. Should we expect the same level of difficulty as the homework problems? It'll be a little bit easier. And so, the homework problems I know are a little bit time consuming. And so in terms of, the complexity, you can probably expect about the same. but the calculations will be shorter to do. Yes. So I'll be modifying the problems so that they're not as time consuming. But you're gonna need to understand all of those concepts of like, moment, summing the forces, and all the trigonometry, geometrical stuff. You should definitely do that. Yeah. Mhm.
Will it be analytical and conceptual problem?
Yes, it'll be both. So there will be a conceptual part. So the conceptual questions are probably about 4 of them. And then for the problem solving questions, you can expect 3 of them. Yeah, so 3 problem solving, 3 analytical, 4 conceptual problems. Yeah.
Are you gonna do one arm, one leg, one lower back? Is that how you're gonna do it?
Probably. Yeah, I think that's yeah, that actually fits pretty perfectly. Yeah. Mhm. Yeah, so I'll put out a study guide probably tomorrow. And then I'll have you guys, just like we did for the first midterm, I'll have you vote on the topics that you think are you need the most help with. And then on Friday, I'll do a review video. Okay, just like I did for the first midterm. So I'll record about a 1 hour video on Friday that you can use, that you can view later on to help you study for the exam. Okay. All right. So you can expect the study guide and the poll to go out tomorrow. All right. Any questions on that stuff before we get started today? Okay. All right. So let's go ahead and pick up where we left off. Okay. All right. So we're looking at linear dynamics of human motion. Okay. All right. And so remember, this set of lecture notes is kind of the immediate follow-up to all of the static stuff that we were doing, right? And so statics, what statics basically means is that it's not moving. And so dynamics is, when we're going to start to look at actual human motion. Okay. And so we start with the linear concepts just because they're a little bit easier to start with. And that's kind of traditionally how it's presented in all your physics classes and previous engineering classes. Okay. And so we're looking at things like linear velocity, linear acceleration, linear position, all of those things. Okay. And so we kind of reviewed all of those concepts last time. Okay? And so the biggest difference is that, before when we did the sum of the forces, right? When in the static case, we set this all equal to 0 because nothing was moving. Okay? The difference here is that instead of adding up to 0, we're going to be adding up to mass times the acceleration. Okay? And so because we have this, since now it's not 0 anymore, now it's mass times acceleration. Generally, what you'll see is that the muscle forces and the joint reaction forces are going to be higher than the static case. And the reason for that is, it's your muscles are going to have to work harder in order to accelerate your body segments instead of just merely keeping them in place. Okay. And so probably the cases where this is not true is when you have an external force that's helping you perform that motion, right? And so let's say that you want to move your arm up, and then if someone's helping you move your arm up, that would be a dynamic case where your muscle forces are less. But generally speaking, you're going to be using your body to oppose stuff on the outside. And so when you're opposing forces and you're doing it in a dynamic fashion, that's going to increase your muscle forces, increase your joint reactions. All right. And where we left off last week was doing a very simple example. Okay. And so the example that we were doing was we had a pull-up bar. And we had a guy here doing a pull-up. This guy just has really long arms, just because I ran out of space. Yeah, super long arms. Right. And so what we say is that this person's mass is 75 kilograms. And let's say that during this part of the pull-up, he's accelerating upwards with an acceleration of 4 meters per second squared. Okay. Okay. And so we performed a force analysis on this. And so we said that the sum of the forces in the y direction in this case has to equal to the mass times the acceleration. Okay. Where the sum of the forces, we have 2 times F because he has 2 hands that he's pulling himself up with. Okay. Right, and then opposing the forces is going to be the weight of the person's body, and so we have a minus mg, okay? And this is going to be equal to the mass, which is 75 kilograms, times the acceleration, which is 4 meters per second squared, okay? And so all of these quantities are known here, except for the F, and so what we get is an F of 517.5 Newton, okay? Yes, yeah. So we're since this motion is purely in the vertical direction, that's why I'm doing some of the forces in the y direction. Yep. So it's sum of F sub y. Okay. And so the upward force that the bar has to input onto the body is 517.5 newtons. And then by Newton's third law, the fact that, you know, there has to be an opposite, equal and opposite reaction, that means the muscles have to pull up or have to produce an upward force of 517.5 newtons. All right. You can compare this to the static case. And so in the static case, you know, the entire right side is equal to 0. Okay. And I'm running out of room. So actually, let me do that on the next page, actually. All right, so are there any questions on this? Okay. All right, so if we compare this to the static case, and so in the static case, the sum of the forces in the y direction is going to be equal to 0. Okay. And so we use the exact same formula as before, except we instead of mass times acceleration, we set it equal to 0. Okay. What we get for the F, the upward force there, is the F static is equal to 367.5 newtons. Okay. And so you can see here that, you know, if the person was just hanging from the bar, then that requires a lot less force than if he was trying to actively pull himself up. Okay. And in fact, you know, it's about a 50% difference. And so if you want to start pulling yourself up, you have to output 50% more force onto the bar. Okay. All right. And so that's pretty, you know, standard stuff, right? So we have a mass, we have an acceleration, and we can compute the force needed to produce that acceleration. We can take this one step further in biomechanics to say that, okay, you know, if that's the force that's going to be applied onto the body from the bar, you know, let's determine what the muscle forces and the joint reaction forces have to be in order to produce this motion. Does the F in question? So does the F in this scenario equal the muscle to keep up the person? Yeah. So this F static right here. This is the force that the bar has to input on the person to basically just offset their weight. Yeah. And so this is the force just to keep the person in. Yeah. Okay. And so in order to produce these external forces, the muscles have to act as well, right? And so we're going to do what's called a pseudostatic analysis, right? And so we talked about this last time. And so under a pseudostatic analysis, we're going to basically compute muscle and joint forces internally assuming that we have a static situation. Okay. I want to be clear here because I'm not saying that the entire situation is static, right? And so external to the body, we have our dynamic situation that we just solved for the forces on, right? Okay. And so in other words, what we can say is that from an external point of view, we're going to apply those dynamic external forces. Okay. Okay. And so for this simple pull-up example, we're actually going to apply the 517 force that we computed on the previous page. Okay. But internally, we're going to assume that the limbs are not actually moving themselves. And so internally, what we're going to do basically the exact same static analysis that we've done before. So we're going to do sum of the moments around the joint. We're going to set it equal to 0. Okay. We're going to sum of the force in the x direction is equal to 0. And the sum of the y forces are going to be equal to 0 as well. Okay. All right. So what we're going to do next is exactly kind of the same thing as we've done with statics. It's just that our external force now is going to be higher because externally we're considering dynamics. And the reason we're doing this is that, when you look at limb motion, like there's no way to really describe the dynamics of it without some kind of rotational dynamics, right? And so for a lot of your body, your joints are in relatively fixed positions, right? And so if you move your arm around, right, your shoulder joint kind of stays in position, whereas your arm kind of rotates around, okay? And so before we can actually talk about, the arm actually, moving and factoring that into our analysis, we need to actually learn about rotational dynamics, which we're not there yet, but, we will get there later this week, okay? And so for now, we're going to do what's called a pseudostatic analysis, where, we're going to apply higher external forces because externally we do have a dynamic situation, but internally we're going to assume that it's static. Okay? And so it's not going to be, 100% accurate. But it will give you a sense of how much harder your muscles have to work when externally you have a dynamic situation. Okay. All right, so that makes sense. Kind of how we're going to approach these analyses. Okay. All right, so let's go ahead and start working on the example. Okay. And so I'm just going to do one arm, and so this is going to be a pseudostatic. Of one arm doing a pull-up. Okay. All right, so here I have the shoulder joint. And so that's the upper arm. And that will be the lower arm. Okay. All right, so we're gonna even though we have two joints here, we're going to focus this analysis on just the shoulder joint. Okay. Okay, and so we have our JX and our JY. Okay. We have our external force here. Okay. And so this external force we've already computed. And so for the dynamic case, this is going to be 517.5. Okay. And then just to show you a comparison between the dynamic and the static case, let me go ahead and put the static number in here as well. Okay. And so this was 367.5. This top one is dynamic. Okay. And this bottom one is static. All right. The muscle force that we're going to consider is FM is going to be for your back muscles actually. Okay. Okay. So this is one of your oblique muscles on the side. So it's kind of pulling your arm downwards. Okay. All right. So let's go ahead and add some angles in here. Okay. And so let's say that this angle right here, this is going to be theta m. Okay, so where theta m is, this one's going to be measured relative to the arm. Okay. And then in addition to that, we have this angle right here. So we'll call this one theta. Okay. And so this theta here is measured relative to the horizontal. Okay. And so remember, when you're doing these problems, you should always kind of check to make sure which angles do you have that you're working with, and what are they defined relative to. Okay. And so let me go ahead and mark this down here. And this is a technique that you can use in your homework too. It's not really a technique. It's just kind of, just being a bit more organized. Okay. And so this theta m here is measured relative to the arm. Okay. So that's one thing good to note. And then this theta right here is measured relative to the horizontal. Okay. All right. Yep.
What about that angle?
We actually don't need that one for this one, because we're not considering any forces in the upper in the lower arm.
If we want the moment or
Yeah. So just to keep the calculation simple, I'm just going to go ahead and give you this moment arm directly. And so the horizontal distance in between the hand and the shoulder, we'll call this LF. But you're right. So if I did give you this problem in terms of the lengths of the arms, you would actually need that. You would need this angle too. But because I'm giving you this length directly, then we don't actually need it. And then just as standard, we have the length in between the joint and the muscle attachment point, and we'll call this LM. Okay. All right. And so just like we always do with these problems, let's compute muscle force and joint reaction forces. All right, so let's do the muscle force first. And so to do that, we're going to sum the moments. Okay, and so if we sum up the moments around the joint, both of the joint reaction forces are going to go away because their moment arms are 0. Okay. And so what we have left is we have a contribution from the muscle force, since we have minus FM Lm sine theta m. Okay. And then opposing this, we have the force from the bar. Okay, so we have FLS. Okay. Okay. And then we're going to set all this equal to 0. Okay. And so remember, this is an approximation, right? And so even though we obviously don't have a static situation, and so we normally we wouldn't sum all this equal to 0. We'd set this equal to the moment of inertia times the angular acceleration. But we'll get to that later this week, probably next week before the midterm. Okay. But for right now, we're going to assume it's 0, just for kind of simplicity's sake. Okay. All right, and so this equation here has only one unknown, and so if we solve for that unknown, we get Fm is equal to FLF divided by Lm sine theta m. Now, if we plug in the numbers for this, okay, we're going to get two answers, one for the dynamic case and one for the static case. And so for the dynamic case, we get 7,565.3 newtons. And then for the static case, we get 5,372.5 newtons. Right, and so you can see that this answer here scales pretty much directly with whatever F is. Okay? And so in the dynamic case, you can see our muscle has to exert about 50% more force than the static case. Okay, maybe it's a little bit less than 50%, but around that amount. But it's pretty significant, right? And so this is a lot of force, especially for an upper extremity muscle. All right, any questions on this? Okay. Sure. Mm-hmm. Can I explain the answer again? Sure. Yeah. So the way we got this answer is basically just a regular moment summation. And so I set it equal to 0 because remember we're doing a pseudostatic analysis. So normally, once we get to rotational dynamics, you would actually set this equal to a term that involves the angular acceleration of your arm. But we haven't learned that yet. And so we're just going to, for now, set it equal to 0. But the way that we make this dynamic is that this F that we're applying right here, we got this F from a linear dynamic analysis. Yeah. So the two answers at the end, one is for dynamic. And so this top one is for the dynamic force. And the bottom one is for static. And the difference is in what we apply for F. Okay. And so for the dynamic case, we set F is equal to 517.5 because that's what we got from the linear dynamic analysis at the beginning. And then for the static case where the acceleration is 0, then we set F is equal to 367.5. Yep. All right, so the muscle force is greater and so the muscle force, that's required is greater in the dynamic case because it takes more work to accelerate versus just, staying still. Okay. All right. And so now let's do the joint reaction forces. All right, so let's do the sum of the forces in the x direction first. Okay, and so in the x direction, we only have the joint reaction force. Okay. And so we're going to assume that that's going to the right. And then we have the muscle force. Okay. But we only need the x component of that muscle force. Okay. And so to get that component, we're going to take the angle theta. Okay. And then we're going to subtract theta m. Because if I draw this image right here, right? So let me go ahead and draw the arm for you. Okay. I'm gonna draw this a little bit exaggerated just to make it look cleaner. And so if this angle is theta right here, okay. Remember the muscle force that we're considering is this one, okay. And the theta m that we're considering is that one right there, okay. And so the reason I'm subtracting these angles is that, you can see here that if we start, always start from a case where everything is completely flat, right? And so if we start the arm completely flat, you can see that we're rotating kind of counterclockwise this way, right? And so that's how we produce the angle, the purple angle theta. Okay, and so you can see that the arrow that the vector that we're working with is kind of moving counterclockwise. Okay? But this theta m is kind of measured below that. And so as we kind of start from here, and then we rotate by an angle theta m, you can see that we rotate around this way. Right? And so these two angles, you can see by this rotation angle right here, and this arrow right here, you can see that they're acting in opposite directions, right? And so when you want to get just the horizontal component, you can just subtract those two angles. So you do theta minus theta m, right? Because one goes this way and the other one's going to rotate it backwards towards the other way. Okay? And so the true horizontal component is just going to be the difference in between those two angles. All right, and so if we plug in FM from our previous step, we can get our two answers for JX. Okay? And so in JX, we get 7,450.4 newtons. Okay? And so this is for the dynamic case. And then for the static case, we get I think there's a typo in my notes. It's 5,000, should be 5,209.9 newtons. Okay. And this is for static. All right, so that makes sense about how we chose that angle there and how we summed up these forces. Okay. All right, so that's the sum of the forces in the x direction. So now let's do the sum of the forces in the y direction, and then we'll finish up the problem. Okay. All right, so for the sum of the forces in the y direction, we have jy. Okay. We have the muscle force. Okay, and so same logic as we did last time, and so we're going to do Fm sine theta minus theta m. Okay. But we also need to add F, right? Because F is the external force that the bar is inputting onto the bar. Okay. And so if we plug in all the numbers for this, we get jy is equal to 796.2 newtons in the dynamic case. Okay. And in the static case, we have 565.42 newtons. Okay. And so for all these cases, you can see that the dynamic case has a higher value. And so generally, once you start to do factor in dynamics, it's going to put a higher amount of strain and a higher amount of stress on your muscles. Okay. All right. And so remember, to perform this analysis, we had to assume that internally our forces were zero, right? Okay. And so under pseudostatic analysis, the rotation of the limbs is not considered. Okay. And so once you add that factor in of the limbs actually rotating, this is going to generally increase the amount of forces that you compute. And so even though with this example, we see that we get a pretty significant boost in the forces in the dynamic case, even this still is kind of an underestimation, because once you factor in, that your limbs have inertia and they have to be rotated, right? And so that's going to require even more forces and more moments. Okay? And so again, we'll deal with all that once we get to rotational dynamics, but I just wanted to kind of make sure that you guys kind of remember that for now. Okay? But even without that factor, you can see that in the dynamic case, we have a pretty significant increase in our forces. Okay. All right, any questions on this before we jump into another example? All right, question: we won't be tested on this, right? Correct. Yes. And so the last set of lecture notes that you'll be responsible for the exam will be spinal biomechanics. Yeah. And so all the dynamic stuff we'll leave it for after the midterm. Yeah, I'll put out a study guide for it tomorrow, but none of this dynamic stuff will be on there. Okay. All right, so let's do another example. And so let's do an example of a track star that's going to jump over a hurdle. Okay. And so let's say that we have a person. Okay. And so they're sprinting as fast as they can. Okay. And he's sprinting towards a hurdle. And so the height of this hurdle is going to be 0.8 meters. Okay. And the distance between the runner and the hurdle is 0.7 meters. Okay. And so we're going to assume that she's going to start her jump, this athlete, when she's 0.7 meters away. Okay. And so basically, we're going to pick up this problem right when she's about to lift off. All right. And so let's say that the horizontal speed that she's running with is 4 meters per second. And so what we ultimately want to compute is the force that her legs have to generate, or her leg muscle forces in order to complete this jump. And in particular, we're going to look at just the quadriceps muscle, I believe. Yes. Okay. All right, so this problem is going to take place in a few different stages, okay? And so the first stage is we're going to look at the linear dynamics. Okay? Right, and our goal for the linear dynamics is kind of, I mean, ultimately one thing, but in order to get that one thing, we have to compute some other things along the way, okay? And so the first thing we should compute is what is the upward acceleration that she needs? Okay? Okay. And then, once you have that upward acceleration, we can then use that to compute how much normal force the ground has to input in order to produce this acceleration. And so those are the two main steps that we're going to compute or do with linear dynamics. And then once we have that normal force, then we can just treat it just as a normal statics problem. Okay. All right, so that's kind of the outline of how we're going to tackle this problem, right? And so first we're going to compute the acceleration that she needs. Then we're going to use that acceleration to compute normal force. And then we're going to take it internally to find the muscle force. Okay. And I forgot to give you something important, which is her mass, right? And so let's say that she has a mass of 63 kilograms. Okay. All right, and so that's how we're going to approach this problem, right? So any questions on that before we get started? Okay. All right, so let's go ahead and kind of follow this recipe here. All right. And so the upward acceleration that she needs, it really depends on when she's going to crash into the hurdle, right? Because she's kind of sprinting full speed into this hurdle, right? And so she needs to jump fast enough so that with her speed, she's not going to trip or run into the hurdle. Right. So first let's compute how much time she has to complete this jump. Before she crashes. Okay. We know from the problem that she's running at a horizontal speed of 4 meters per second. Okay. And her distance, the horizontal distance between her and the hurdle is 0.7 meters. And so we can take these two and we can find their the ratio to compute time, okay? And so if we take the 0.7 meters that she has until the hurdle, and we divide it by her horizontal velocity, then we get a time of 0.175 seconds. Okay. Right? And so she's sprinting really fast towards the hurdle, and then she's gonna hit the hurdle in about 0.175 seconds. Okay. And so in that time, she needs to jump fast enough so that she clears the hurdle. Okay. Yep. We do actually. So I kind of just we did it very quickly. And so the formula that I use for this is x is equal to xo plus vt plus 1/2 at squared. But I set this equal to 0, and we're not accelerating in the horizontal direction, and so we said x is equal to vt. So t is equal to x divided by v. That is a good segue though, because we are going to use this. And so that's kind of the kinematics in the horizontal direction. Now we need the kinematics in the vertical direction. Okay. And so we're going to apply this kinematic equation in the vertical direction now to compute the upward acceleration that we need. Okay. All right. And so if we say that y, I'm just switching to y just because we're going vertical now. Okay. Plus vt plus 1/2 at squared. Okay. I'll call this v naught t actually. Okay. All right, and so in the vertical direction, we know that our hurdle is 0.8 meters tall, right? And so let's go ahead and substitute that in for y right here. And so we know that. Okay. Y naught, we're just going to set equal to 0 because we're going to assume that we start at ground level. Yeah, she has to jump quickly. Yeah, it's amazing because I think when you're watching like Olympic hurdles, at least for me, of course it looks impressive, but you don't really think about how much force that they have to generate and how quickly they have to kind of move their bodies just because of how quickly they're sprinting. Yeah. Because it's because her feet have to clear the hurdle. And so we were saying that her feet, if we're measuring everything from her feet, we're saying that her feet has to come up 0.8 meters. Yeah. Mm-hmm. All right. So we're going to assume that she doesn't start with any upward velocity, and so she's kind of just on the ground at first. Okay. And so we're going to cross out that term. Okay. We have t because t is what we just solved for, and so we can use this equation to solve for a. Okay. And so a, which is going to be your upward acceleration, is going to be 2 times y divided by t squared. Okay. Right. And so if we plug in y is equal to 0.8 meters, and then t is equal to 0.175, what we get is an upward acceleration of 52.24 meters per second squared. And so she has to accelerate in a hurry, otherwise she's going to run into the hurdle. Okay? And so her legs have to generate enough force such that she accelerates upwards with an acceleration of 52.24 meters per second squared. All right. Any questions on this?
Oh, I'm sorry, I lost. I wasn't paying attention for a moment there. Why is VOT canceled?
Yeah. So this kinematic equation that we're using, this is in the vertical direction, and so when she's just running towards the hurdle, on the ground, she doesn't start with any velocity going in the upwards direction, right? Because she's just running on the ground. And so this VOT that represents, what her initial velocity is once kind of when we're taking the snapshot. Right? And so because we're taking the snapshot right before she takes off, she doesn't have any VO.
I see. Thank you.
Yep. If she had a jetpack, would we consider VO? Yes. Yeah. And so if she had a jetpack and she was already moving upwards when we're computing this, then we can put that in for VO. Yeah. But this is normal. This is normal Olympics. This is not futuristic Olympics. That'd be interesting to see if we have an Olympic competition with like extra technology like that. I'd like to see that. Okay. And so now that we have this upward acceleration here, we can use that to compute the force, right? Okay. And so the normal force or the upward force that the ground has to produce is going to be her mass times the acceleration that we just computed. And so the mass, remember, is 63 kilograms, and her acceleration is 52.24 meters per second square. Okay, and so we multiply these two, we get 3,291.12 newtons. And so fairly significant, force, right? Because it's a fairly high acceleration because she has to clear this hurdle in such a short amount of time. Okay. All right. And so, before we jump internally, let's go ahead and classify this force before we go. Okay. And so this 3,291, remember, this is the external force that the ground is exerting on the person in order to get them to accelerate upwards. Okay. Okay. Right. And so now what we can do is we can perform our pseudostatic analysis with this external force acting at the foot. Okay. All right, and so let's go ahead and draw our free body diagram. And so let's say that's your thigh. This is going to be your lower leg. Okay. This is your foot. Okay. So this person has a very tiny foot, apparently. Okay. All right, and so in order to jump, this person, the ground has to exert a normal force here, and that's going to be the normal force that we just computed. So this can be 3,291.12 newtons. Okay. And so producing this force is going to be a muscle force. Okay. And so we're going to be considering the quadriceps muscle because the that's the one that mostly works on leg extension. Okay. And let's say that the angle with respect to the horizontal here is given by theta. So a little bit different, but this will make it a little bit easier for our calculations. Okay. And to kind of further make it easier for our calculations, let's assume that we're given this moment arm. Okay. And so the moment arm between the muscle force and the knee joint, we'll say this is Ln. And so we don't need any trigonometry to compute the moment arm. Okay. And similarly, let's say that the moment arm in between the normal force and the knee joint, that's going to be given to us as well. And so let's say that's Lj. right? And so at least for the first part of the problem where we, compute the moments, we're not going to need any trigonometry. Okay. Yeah.
Is your quad really attached to that model?
It's a little bit exaggerated, but it does pass over the patella, and then it does attach onto your shin. Yeah. Mhm. Yeah. This is a little bit exaggerated, but normally, maybe it attaches maybe somewhere around right here.
I always thought it was like above.
Yeah. In order to extend your lower leg, it has to attach onto it. Yep.
In order to actually move your shin, you have to fix it somehow.
Yep. Mhm.
And is that like, so is it the actual, it's not any of the actual meat of the muscle, is it just like the tendon that's connected to the quad that then attaches to your?
Yeah.
Almost like a cable, right?
Yeah.
Then just using the force gender where it comes.
Exactly. Yeah. Yeah. So it's mostly the tendons, but yeah, the most of the meat or the most of the motor units for the quad is actually in your thigh. But the tendon does stretch over your patella and attaches to your shin. Yeah. Mhm. Okay. And then we have the joint reaction force in the X direction, and then the joint reaction force in the Y direction. All right. And so just like we've done before, let's go ahead and compute the muscle force and the joint reaction forces. Okay. And we're going to do this with pseudostatic analysis. Assuming that internally everything sums to 0, but we know that externally, things are moving. But this is just for the simplicity of the analysis. All right. Any questions on the setup here? Okay. All right. And so let's start by summing the moments. Okay. So we have the sum of the moments around the joint. And since we're given the moment arms exactly, we can just say that the moment as a result of the muscle force is going to be FMLM. And then the moment due to the normal force from the ground is going to be FNLJ. Okay. And so we solve this equation for FM. We get FM is equal to FM times the ratio of LJ over LM. Okay. Oh, I didn't give you any values for these parameters. Huh? All right, so let me give you the values of these parameters. And so we'll say that LM, we'll say 6 centimeters. And then LJ, let's say this is 15 centimeters. Let's see, it hasn't shown up yet, but we'll say that the angle theta angle is 30 degrees. Okay. And so I think that's all of the lengths that we need. Okay. All right. And so if we perform this calculation, what we get is FM is equal to 8,227.8 newtons. Okay. All right, and so now we can sum the forces in the X direction. And so in the X direction, we get JX plus. And since this theta that we're given, this theta is with respect to the horizontal. Okay. And so since this theta is with respect to the horizontal, that kind of makes our life a little bit easier. And so when we sum the forces in the horizontal direction, all we need to do is just add a cosine theta. Okay. And of course, this is equal to 0. And so we solve for JX, and we get that JX is equal to minus 7,125.48 newtons. Okay. right? And so that tells us that Jx is actually, it should actually be pointing to the left, right? And so whenever you get a negative force, all that tells you is that, you know, it should just be pointing the opposite direction, right? And so that's fine, you know, because you know, when we drew our free body diagram, we drew Jx and Jy in kind of an arbitrary direction. And so we didn't, you know, in this case, we could have put it the opposite direction. But you know, you can do that. And so you can put your joint reaction forces in an arbitrary direction. It's just that when you compute it and you get a negative number, you just know that it should be pointing the opposite direction. But you know, that's fine. Okay, and so we have Fy. And so for Fy, we have the contributions from Fj, or Fn, I'm sorry. And so we have Fn, which is the normal force from the ground, okay, plus Fm Fm sine theta plus Jy, okay, and this is equal to 0. Okay. Right, and so if we solve for these forces, what we get is Fy is equal to minus 7,405.02 newtons. Okay. And so once again, you know, the joint reaction force, I should say this is Jy, I'm sorry. There's a lot of chatter outside, it's kind of distracting me. And so and so this tells us that the joint reaction force should also be going in the opposite direction. Okay. Yeah, so if you get a negative number for your joint reactions, all you have to do is just, you know, you just say that it's supposed to go in the opposite direction. That's fine. Yeah. Mm-hmm. Yeah, so that's totally fine. And so on the exam or something, if you get a negative joint reaction force, you know, don't panic, don't redo the whole problem. You know, just say that, you know, the direction is just opposite from what I indicated in the figure, and that's totally fine. Okay. All right, any questions on this? Okay. Right, so dynamics is, you know, linear dynamics is, you know, I think not that big of a step up from statics because, you know, we're still doing the same kind of static analysis. The main difference here is that the external force that we compute, or the external forces that we use, you know, oftentimes we compute this from some kind of linear dynamic analysis. Right? And so it's almost like an amendment, or not an amendment, or just a little bit of extra work than what you have been doing for the statics, and that involves the linear dynamic stuff. Okay? All right. And so, you know, now that we have the main quantitative stuff out of the way, let's talk about a little bit more linear dynamic concepts that can help us, you know, before we move on to rotational dynamics. All right, so first let's do kind of a quick refresher of the ideas of momentum, impulse, and impacts. Okay. All right, and so, you know, another, you know, in addition to displacement, velocity, and acceleration, another really important concepts in linear dynamics is, you know, momentum. Okay, and so let's define momentum first. Okay. And you know, you'd be surprised. You know, momentum is actually a little bit of a difficult term to define. Okay? But but kind of the textbook definition of momentum is that it's a quantification it's a quantification of the amount of inertia a body has. Hang on, this is bugging me too much. And so let's go ahead and define inertia. Okay. And so inertia basically quantifies how hard it would be to change an object's motion. Yeah, has. Sorry. Yep. Mhm. Yep. And so inertia describes how hard it would be to change an object's motion. Okay. Right. And so remember, remember Newton's laws, right? And so Newton's laws, what it basically describes is when an object starts and gets to be in motion, okay, you need to apply some kind of external force in order to change its motion. Okay. And the way that we quantify all these quantities is through momentum and inertia. All right. And so mathematically, the way that we compute momentum is just the product of an object's mass multiplied by its velocity. Okay. And so I've seen, all different kinds of symbols for momentum, but I just use capital M. I know it's a little bit confusing with moments, but I just like a capital M for momentum. Okay. Okay. And so momentum is just going to be mass times velocity. Okay. And so, it's even though it's a little bit obvious from this equation, but we can just state it just to be complete. A static object, or one that's not moving, has no momentum. Okay. All right, and so these ideas of momentum and inertia are really important for dynamics in general, right? Mostly through the act of two important laws. And so first we have the law of conservation of momentum, and then we have the force impulse theory as well. Okay? And they both kind of act on this idea of inertia. Okay, any questions on this? Okay. All right. And so one particular application where momentum is really useful is for describing how different objects interact with each other in terms of their motion. Okay. Right. And so in particular, we have the principle of conservation of momentum. And so the conservation of momentum is that in the absence of external forces, In the absence of external forces, the total momentum of a given system remains constant. Okay. And so mathematically, what we can say is that the momentum in one state, okay, is equal to the momentum in another state, okay, given that no external forces are acting on it. Okay. And so what this is saying is the product of mass and velocity in one state is equal to the product of mass and velocity in another state. Okay. All right, so how do we see this this principle in action, right? And so let's say that we have a system of two billiard balls, well, of two sticky balls, colliding with each other. Okay. And so let's say that we have one ball going this way, another ball going that way. Okay. And so overall, this system has a certain amount of mass and a certain amount of velocity. Okay. Once these two balls collide, right, then eventually, they're going to move off, together, right? And so let's say that they eventually move off towards the right. Okay. But their ending velocity, okay, their ending velocity is a function of what their beginning velocities were, as well as their masses. Okay. Okay. And so if you consider their momentum together, in the first phase, then you can find out what their momentum is in the second phase, okay, after they've collided. Okay. And so, you've probably seen a problem like this in your previous physics classes. So, I won't go through the mathematics of it. But kind of maybe a biomechanics example of this is, maybe you have two hockey players that are skating on the ice toward each other, and then they just collide with each other, right? And so after they collide, human bodies are relatively, elastic, and so they're not going to bounce, maybe not too much, but let's assume that they stick together, and then after they kind of stick together, then they kind of move off in one direction. All right, any questions on this? So hopefully this is kind of just review from physics from everybody. Okay. All right, and so with that said, let's talk about the force impulse principle. And so conservation of angular momentum or conservation of momentum is when we have no external forces acting on an object, right? When you do have an external force acting on it, it's going to change the momentum of the object, okay? Okay. And specifically, the amount of momentum that changes depends on the product of the, or depends on how long this force is acting on the object. Okay. Okay. And so what we have is the force times the time is equal to the momentum in the final state, and so we'll call that mv2 minus the momentum in the initial state, mv1. Okay. And so, think about, at least for us in the classroom, we have the roller chairs, right? And so the roller chairs, one way you can change the momentum is by pushing it, right? And so if you're applying a constant force onto the chairs, the ending momentum or the amount of speed that the chair picks up depends on how long you're going to be applying that force, right? And so if you apply that force for a very short amount of time, so let's say that you just kind of tap the chair, it's only going to move forward just, with a small velocity. But if you keep pushing it and pushing it, it's going to keep speeding up and speeding up, right? Hence its momentum grows from that, okay? All right, and so what we'll learn on Wednesday is, the body actually utilizes this, and you kind of, instinctually kind of understand this force impulse principle to kind of help protect your body in a lot of, dangerous dynamic situations, okay? And so we'll do an example of, if you jump down from a high place, and we'll talk about how your body utilizes the force impulse principle to minimize the amount of damage on your joints and your muscles, okay? All right, any final questions before we wrap it up for today? Okay, all right, and so that's all we got time for. And so we'll pick this up on Wednesday. And so hope everyone enjoys the rest of their evening. Remember, keep an eye out for the study guide and for the review poll tomorrow, right? And I will see everyone on Wednesday. Yep. Sure. Yep.
Is this like the first derivative one or the second one?
Yeah, it is. Yeah. It's the integral of it. And so if you integrate the if you integrate f is equal to ma, then you get mv.
Yeah, I guess that's a better way to say it.
Yeah. Yeah. And actually, this force impulse is kind of a simplified version. And so, normally you would take, the integral of f dt, right? And so this is actually the true force impulse form. Right, and so you take the integral of f times the integral of f over dt, and then that ends up being your momentum. But we simplify it to this algebraic form up here, just because this is a little bit easier to evaluate than an integral.
So what came first?
Yep, no problem.
Do you know what came first when it was coming up with all this stuff? Did he come up with the momentum first? Yeah.
That's a good question, actually. I'm not sure. I would assume that he kind of first observed things in the world and kind of maybe thought of the first one just in his head, but when he sat down and formalized it into math, I think he probably presented it as the second one. Yeah.
Are we doing an activity today? It's 5:40.
No, we're doing one on Wednesday. So today we're going to learn about the theory behind it, and then Wednesday we'll put it into action. This week is pretty cool. I think well, it'll be a lot of sitting around doing nothing, but the theory of what's happening is really cool.
Okay. So is the final project going to be static structural?
Yes.
Okay.
Yeah.
Yeah.
Yeah. I'm kind of debating a little bit because I know some people are in the class are coming from like a work industry perspective. And so I want to give them a chance to perform an analysis on, maybe something that they're working on. But I also want to keep the grading a little bit consistent too. And so I'm deciding whether to give some geometries like the midterm project, but also give an option for external CADs as well. But I'm deciding because that becomes a little bit harder to grade if it's everyone's doing something different. So, but yeah.
All right. Sounds good. Do you know when we're gonna get that?
Probably sometime next week. And so I am a little bit busy this week because I have to grade the midterm projects, but I do want to give it to you guys at least a couple of weeks before Thanksgiving, just so that you have over a month to work on it, just like the midterm project.
Yeah, because I think I'm gonna try to like start writing mine a lot earlier this time, just because like I don't know, I had my goal in mind, and then when I started writing it, I'm like, I don't know, it sounds kind of dumb. Like I just wasn't like I'm not used to writing in that style. I found myself wanting to use like my old liberal arts style of writing that I'm used to, and so I'm like trying to make it sound like you know, the papers that I've read in the past, which are not very many.
Mhm.
So like, I feel like I need to start it much, much earlier. So like, can you read it and kind of give me an idea? If I write it down early enough, can you read it and kind of give me an idea of where I'm going wrong and like what kind of language I should,
Sure.
and grammar I should be using?
Yeah.
Because,
Yeah,
you know,
I can do that. It'll be a little bit of a lower priority item for me just because I
Yeah.
have, you know, other stuff too, but you send to me early enough, then I can get around to it. If you send to me
Okay.
before, like, if you can send it before Thanksgiving, actually, that would be the best because I
Okay.
do have a lot of free time over Thanksgiving. I can give you feedback.
all right. Yeah, because like I was really satisfied with my ANSYS analysis, but then when it came to like putting it down on paper, I was like, how do I convey this in a way that, you know, makes sense?
Mhm.
And like with my goal and all that stuff, so. All righty, thanks, Professor.
Yep, I'll see you in class.
See you in class.